this is my name. I'm from the Chongbuk National University. Today, let me talk about the photocatalytic water decomposition for the hydrogen production over titanium sulfide supported on the titanium silicon mixed oxide. First of all, let me show the objective of our work. As I mentioned in the title, I employ the titanium silicon mixed oxide as support. So we will wonder why we employ the titanium silicon. Let me back from the 1972, after the discovery of Fukushima and Honda, for the photocatalytic water decomposition over titanium electrode under radiation. From then, various kind of catalysts has been explored so far, especially the mixing of titanium and silica physically and chemically to obtain the synergistic effects. For example, we can obtain the neutron state exercise or warm side effects and support effects for titanium silica compared to titanium alone and bare silica. But we wonder how about the synergy effects in the electronic properties of titanium silica. For this reason, in this work, we try to carry out the flat band potential determination and doubling density, I mean the carrier density in the titanium silica compared to titanium and silica alone. We also try to determine the influence of this synergy effect on the photoactivity of titanium sulfide over titanium silicon mixed oxide. Now let me show you about the principle of photocatalysis. We know under the radiation, the electron in the photocatalyst will from the valence band to the conduction band, and from here, electrons and the holes will encounter the recombination in the bulk of photocatalyst or on the surface of photocatalyst. Another way, free electrons and free holes will carry out the reduction or oxidation reaction. For example, in our case, the electron will reduce the proton to produce hydrogen, and the electrons here, the hole here will oxidize water to produce oxygen. To replace titanium silicon mixed oxide, we employ the two-step method with the rehydrolysis of TiO2 and water. After that, we mix with TTIB and under hydrolysis and condensation, as in drying calcination, we can obtain the titanium silicon mixed oxide. To support the ruthenium sulfide over titanium silica and silica, we employ the impregnation method with reduction under the hydrogen flow and sulfidation under the hydrosulfide hydrogen flow. Of course, after calcination, we can obtain the supportive ruthenium sulfide. To carry out the characterization of the electronic properties of titanium silica, photocatalyst, we have to repair the working electrode. And why we need to repair the working electrode, I will talk to you later. We mix the solvent and photocatalyst. After mixing sonication, we coating this dispersion over the working electrodes. After drying in air and binding by neutron solution and drying again in oven, we can obtain the working electrode. Now let me show clearer about the working electrode view here. This is my catalyst layer coated on the plastic carbon disc in connection with the metal wire, and this working electrodes will be connect to the electrochemical system. In this case, we employ the 3 electrodes, electrochemical compartment cells, and this system will be coupled with the locking amplifier and potential start to determine the capacitance of photocatalyst. Now let me show briefly about the electrical circuit for the potential step. To determine the capacitance, we have to apply the potential over the working electrode lambda ampere already. In this case, working electrode will be in reality to the reference electrode. In this case, I use the silver chloride reference electrode. Under potential applied here, compared to the counter electrode here, I employ the black and white. To make the circuit, I can determine the capacitance of the photocatalyst. To determine the flat band potential and also the doping density of the photocatalyst, we have to use the measurement of the capacitance and the voltage in connection with the application of the Moskowski equation. We can see here so clear, if we approach the capacitance -2 to 0, we can see the right hand side will be approach to the 0, 2. From this, we can determine the flat band potential of photocatalyst. And we also, on the other hand, we can see the slope of this equation. If we can draw out, we can figure out this plot, we can determine this slope. If we know this slope, we can determine the ND. ND is the doping density, because here is just a constant, for example, dielectric constant. This is for material, and the permittivity is a constant for every material. Now let me show one of the figures about the capacitance measurement of the titanium silicon mixed oxide versus frequency at different frequency and at the fixed DC potential, in this case 0.1 volt. And from this figure, we can draw out the Moskowski plot. For example, in this case, the Moskowski plot of titanium at different frequency. And with this plot, we can interpolate the plot to the 0 value of the C-2. From here, we can determine the potential, the flat band potential of titanium. And this figure shows all of the Moskowski plots of titanium silica alone and titanium silica mixed oxide. And from this figure, from the interpolation and from the slope of this plot, we can obtain the bandwidth, I mean the flat band potential of titanium silica and titanium silica mixed oxide here. Clearly, we can see the synergistic effect on titanium silica compared to titanium and silica alone, with a little much higher on flat band potential of titanium silica compared to bare titanium and silica. From the slope of the Moskowski plot, of course, we can obtain the doping density. We also see the synergy effect here for titanium silica, 1 order higher than silica and 2 orders higher than titanium alone. This SD pattern just I'd like to confirm the amorphous phase silica and the relatively high crystallinity of titanium, in this case B25, and a medium crystallinity of titanium silica oxide. In this figure, I'd like to remind you about the synergy effect in the band gap energy of titanium compared to titanium and silica alone. In this case, we can see the band gap energy higher than, of course, titanium and silica. And furthermore, the specific surface area of titanium silica and silica also higher than titanium. But if we dop the ruthenium sulfide here, the surface area will be decreased significantly because of the very low specific surface area of ruthenium sulfide. To test the photoactivity of our catalyst, we use this reactor system for the decomposition, UV lamp under the cooling system water here, and the water and photocatalyst is under sterile. We control the whole system around 30 degrees C, and the hydrogen and oxygen will be analyzed by GC. Where let me show the photo activity in correlation with the band that I determined later before. We can see here the highest activity of titanium silica compared to titanium and silica alone is very well supported by the band position of titanium silicon oxide compared to silica and titanium. Another figure I like to talk about the ruthenium loading effect in this case. From 0 to 1 weight percent, we can see significant increase of the photoactivity of catalyst. But if we increase the weight percent of ruthenium sulfide until 4 weight percent, we can see almost trace amount of hydrogen formation here. From this result and from the, we can have from the K-Hara paper, we can give our association from 1 weight percent of ruthenium sulfide over titanium silica. We can see the flat band potential of ruthenium sulfide higher than the redox potential of hydrogen. Compared to 4 weight percent, the flat band potential lower than the redox potential of hydrogen. This is one way for explanation, and the common way for explanation when the photoactivity decreases, when we increase the composition of ruthenium sulfide is that when we increase the composition, roughly the ruthenium sulfide will be the trap to so that the electron and the holes in the photocatalyst easily recombine. That's why the photoactivity of catalyst decreases when we increase the composition of ruthenium sulfide. But in our case, we try to use this explanation different from the common explanation. Now let me show the support effect in correlation with the gas. We can see here also the very high photoactivity with titanium silica as above compared to titanium or silica as above. It's very well consistent with the band disposition of titanium silica compared to silica and titanium alone. As we know from the fact that alone titanium silica and alone titanium sulfide, the photoactivity is very low. But if we don't ruthenium sulfide over titanium, we can obtain very high photoactivity. For that reason, we suggest the charge transfer in this system. The electrons and the holes from titanium will move to the ruthenium sulfide, and from here we can see the hydrogen on both titanium silica and ruthenium sulfide will be produced. For this charge transfer, we can see the recombination between electrons and the hole will be suppressed. That's why the efficiency of the catalyst will be increased. The final figure, I'd like to show you the sacrificial effect. We employ various kinds of sacrificial here, but the photoactivity for the hydrogen evolutions, we can say almost similar. Meanwhile, in combination between the sodium sulfide and sodium sulfide here, we can see significantly increase of the photoactivity. For the explanation about this phenomenon, we can say the synergy effect in sodium sulfide and sodium sulfide here. Furthermore, it's also very well known that this Na2S very good to increase the flat band potential of ruthenium sulfide over titanium silicate. For that reason, this combination increase the photoactivity of the whole system. As a result, we can observe the high evolution of the oxygen and hydrogen. Okay, let me summarize our work. We can see the synergy effect of the flat band potential and the double density of titanium silicon mixed oxide as either catalyst or as a support. And from this synergy effect, we can see the substantially improved photoactivity of catalyst. When we increase the chemical loading over titanium silicon over 1%, the photoactivity decreases significantly, probably due to the decrease of reduction potential of ruthenium sulfide. And the combination between the sodium sulfide and sodium sulfide here as a repeat reaction, we can obtain exceptionally improved hydrogen formation over photocatalyst.